Now in this first term which we have discussed, we can, if I multiply with z power minus n and z power plus n here, then there is no problem in this. We can just try and manipulate z power n and z power minus n here, and we get this. Now if you combine these two factors here, you have z power n sigma k 0 to infinity x of kt plus nt z power minus of k plus n. Now in this equation, for example, I am trying to do it like this. In this equation, if I add these terms, if I consider z power n into these terms, now you can say we can add this term here, k0 to n minus 1 x of kt z power minus k minus sigma k0 to minus k0 to n minus 1 x of kt z power minus k within the brackets. Now if you have any doubt in this, I will try to once again represent this entire term. I try to replace this equation that by definition of z transform x of t plus nt, k is equal to 0 to infinity x of kt plus nt z power minus k. For this, if I multiply z power minus n and z power n, then I can write this equation as sigma k is 0 to infinity x of kt plus nt z power minus k plus n, and z power n I can bring it outside of the summation. And now if I consider z power n and take the bracket inside, and sigma k is 0 to infinity x of kt plus nt z power minus k plus n plus, now if I add this term k is equal to 0 to n minus 1 x of kt z power minus k minus sigma k 0 to n minus 1 x of kt z power minus k. Now these two factors should be clubbed when we are having this term sigma k, these two factors, factor 1 and factor 2, both these combined together, we can write it as x of z, because for k and factor 1 and factor 2, you can consider this as factor 1 and this as factor 2. Now when k is equal to 0, what is this? You will have x of nt z power minus n, and infinity you have the next term. Up to infinity you will have this term, that is x of infinite t z power minus n. You have this term. Then this factor term, when k is 0, you have x of 0, and as this is going, x of n minus 1 z power minus n. Therefore you have this x of 0, x of n minus 1, x of n to x of infinity. Therefore you can club these two together. You have this k is from 0 to infinity x of kt z power minus k. If you add these two, you will get this term, which is nothing but x of z. Therefore after replacing this with this term in the braces, you can have z power n into x of z, and the last term minus sigma k is 0 to n minus 1 x of kt z power minus t. This is the z transform of x of t plus nt. Now using this is a time advanced z transform of any function. Now for example, let us say a unit step function is time delayed, or a unit step function is time advanced, or you can say, for example, let us say z transform of x of t plus, when n is equal to 1, t plus nt. That is z into x of z minus, when n is equal to 1, k is equal to 0. So you have only one term there. So x of 0, z power minus 0. That is, you have z x of z minus z x of 0. Similarly, z transform of x of t plus 2t, what do you have here? Z square into x of z minus sigma k is 0 to 2 minus 1, it is 1 and 2, therefore sigma k is 0 to 1 x of kt z power minus k, which when we elaborate this, we have x of z minus k is 0, it is x of 0 minus x of 1 or x of t z power minus 1, or you can elaborate this as z square x of z minus z square x of 0 minus z x of 1 or t. That is how we can, therefore, after looking into this, you can generalize any statement. Generalize x of t plus nt, you can write z power n x of z minus z power n x0 minus z power n minus 1 x1 minus so on z power 1 x of n minus 1. Right. So you have this statement until this point. Now for example, we can consider both this time delay function and time advance function. Time delayed and time advance function, we have z power minus n x of z. Now you have this as the time delayed function z transform and time advanced, both these combined together, you can call it as real translation theorem. Both this put together, you can call it as real translation theorem. And for example, the z transform of a unit step function, we got 1 by 1 minus z inverse, or z by z minus 1. Now what is the unit step function of u of t minus z transform of u of t minus t, which is a time delayed unit step function? The function is of this form. At time t is equal to 0, this is u of t minus t. Now what is the time delayed function of this? That is, as for this equation, it is delayed by 1 second, therefore z power minus 1 into, what is x of z? It is 1 by 1 minus z inverse. Therefore you can call it as z inverse by 1 minus z inverse, or 1 by z minus 1. Or similarly, if it is delayed by 4t, this is u of t minus 4t. Therefore u of t minus 4t is given by z power minus 4 into 1 by 1 minus z inverse. Therefore I will get z power minus 3 by z minus 1. Now we will have a look into this complex translation theorem. So far we have discussed in the shifting theorem we have discussed real translation theorem. We will now look into the complex translation theorem. Complex translation theorem, which is nothing but if you consider e power minus at into x of t. What is this z transform of e power minus at x of t when z transform of x of kt is equal to sigma k0 to infinity x of kt z power minus k. Right. So according to this equation, you can say by definition z transform of e power minus a kt x of kt gives us by definition sigma k is from 0 to infinity e power minus a kt x of kt z power minus k. Now if I just simplify this function, k is from e power 0 to infinity x of kt into e power a t z power minus k. If we can replace e power minus a kt and into z power minus k in this form, you can say that this is x of e power at into z. So the answer for this is x of e power at into z. So instead of z, you replace with z into e power at. It is e power at is a constant. So this is your complex translation theorem. Now let us consider an example of